let's go through the case of resonance. Maybe the most familiar example with from real life would be the simple swing, right? So basically, resonance here means that when the swing is moving forward, you try to push it forward further, and when it is moving backward, you apply force to push it backward even further, and that's why its oscillations are increasing in amplitude. So, but strictly speaking, spin is a little bit, sorry, the swing is a little bit different. Its differential equation is a bit more complicated because here we don't have a spin, and instead we have like an angle theta. So if this angle is theta, so theta of t, then the differential equation here is going to be nonlinear. There's something like theta double prime plus some coefficient, say, I don't know, a times sine theta is 0. So that's the equation. But the concept of resonance, I think the physical intuition here is very similar. So let us figure out the mathematics behind resonance. Right. So suppose that we have our initial value problem, and suppose that now the frequency of the driving force, which is in the right hand side of our initial value problem, is the same as the natural frequency of the spring mass system, right? So this omega 0 is just square root of k over m, right? Then this is a non-homogeneous equation, so let us use the method of variation of parameters. Oh, and last week we have derived this scary looking formula. So the Rons can be computed. So now I have just substituted everything that I know into the formula. And here is U1, here is U2. Wow, that looks complicated, surely. But then now U1 of t is this thing, where this is U1, and this whole thing is U2. So it is even more complicated. So here is the solution. Wow. And that's just a particular solution of this equation. So the general solution of this equation would be this whole thing plus C1 cosine omega 0t plus C2 sine omega 0t. So it is really huge. Wow. But it is not so bad as you might think. So here is a little problem for you to figure out and discuss online. Show that this formula can actually be simplified. So this is, of course, much simpler. Okay, and here is the answer. So that's the general solution of the differential equation. So notice that here, this part is just simple oscillation, right? But this part, here we have times t. And times t means that, so because of this sine function, we have oscillations, but every time we do times t, and which means that these oscillations, they increase in magnitude as t goes by. So as t becomes larger and larger, the oscillations increase in magnitude. For instance, you can, if say our initial condition is that u of 0 is some number c1 and u prime of 0 is say 0, then we get this formula. And if we plot the graph of the function u of t versus t, so let me write that this is, suppose that this is u, this is t, then notice that here oscillations, all the oscillations, they are squeezed between two lines, and these are, of course, lines u equals f0 t over 2m omega 0, and u equals minus f0 t over 2m omega 0. Right, so in case of a resonance, when the frequency of the driving force is the same as the natural frequency, yeah, then oscillations linearly increase in amplitude. And for instance, here is the example plotted here. And again, if you want to explore the topic further, I have created some simple graphs in Desmos calculator, so you can click here and play with the graphs if you want. So you'll have to open the PDF lecture notes to do that. All right, so just one more example. In the left plot there is no resonance, and in the right plot we have a resonance, but with damping, right? So without damping, resonance would increase, to infinity. So with damping, we would have this, but without damping, of course, the damping force prevents oscillations from just becoming too bad. And then eventually, in the beginning, the damping is not important, but then oscillations are increasing. So, and then at some point, they are still quite moderate. So that's the highest possible, largest possible oscillation.